So 5.18, steam enters a two-stage steady flow turbine with a mass flow rate of 22 kilograms per second at 600 degrees Celsius and 5 megapascals. The steam expands to a saturated vapor of 500 kilopascals, where 8% of the steam is removed for some other use. The remainder of the steam continues to expand all the way to the turbine exit, where the pressure is now 10 kilopascals, the quality is 88%. The turbine is assumed to be adiabatic. Compute the rate of work done by the steam during the process, neglecting the change in kinetic energy. So this is quite a bit to unpack. So what do we have? We have a turbine, which we're used to, that's good. And then for some reason, we have a second turbine because it's a two-stage process. So we start at state 1, we go to state 2, and then we go to state 3 like this. And somewhere in the middle, we say 8% of the steam is leaving the system entirely. So it's a little bit more complicated than what we're used to. So we want to find the work output. Now, both these turbines are doing work. So one thing we might want to do is say, okay, well, let me just treat it like some separate problems. I'm going to look at the work here. I'm going to look at the work here, and that's the total work done. But of course, this gets a little bit complicated. I mean, it's not even the same mass flow rates, right? Going from 1 to 2 is 22 kilograms per second, but going from 2 to 3 is only 92% of that, right? Because 8% is leaving. So a much simpler way of doing it is treating your system, because you get to define your system, as the two turbines together. And let's just draw that as a box. So let's say this box represents your whatever is going on in there, both turbines combined. We don't even really care the specifics, but all we know is what goes in and what comes out. So what goes in is that 22 kilograms per second at state 1. And what's coming out? Well, of course, we leave at state 3. But we also have that 8% stream that's coming out in between. Right? Now, if we apply the first law of thermodynamics, we're just looking at an energy balance. What goes out minus what goes in. So Q, we're told, is 0 minus W dot, and that's what we're trying to find, equals, what's M dot out? Well, let's call this actually 1, 2, 3. So M dot 3 being the mass flow rate that leaves the second turbine times the enthalpy as it leaves that turbine, plus the mass flow rate 2 times the enthalpy. And that's, of course, referring to that small 8% that gets taken away in the middle. And of course, minus what goes in, which is the full 22 kilograms per second times the enthalpy there. So we're going to go and try to find H1, H2, H3, M dot 1, M dot, sorry, these should be dots, M dot 1, M dot 2, M dot 3, and see if that's possible, and then we can find the work. So M dot 1 is given as 22 kilos per second. M dot 2, we're told, is 8% of that. Okay, so 0.08 times 22 is 1.76 kilograms per second. And M dot 3 is what's left over. So you can either do 22 times 0.92, or you could do 22 minus 1.76. Either way, you'll get 20.24 kilograms per second. Now, you always want to make sure, in this case anyways, that M2 plus M3 is equal to M1. All the mass has to be accounted for. So in this case, it is, and that's good. If it wasn't, though, we'd know we made a mistake somewhere. So anyways, we have all our mass flow rates, so that's good. Now let's talk about the enthalpy. Well, this is just, it's a steam turbine. This is just going to the tables. We're used to this. We know how to do this. So in state 1, let's see, state 1 is 5 megapascals and 600 degrees Celsius. So if we go here, it's going to be a steam. So it's, lost it. There we go. 5 megapascals and 600. So following this line here, 366.5. So 6665. kilojoules per kilogram. Okay, what about H2? Well, we're told it goes to 500 kilopascals and it's a saturated vapor. So let's go to the mixture tables and look for 500 kilopascals, so 0.5 megapascals, saturated vapor. And this is the enthalpy we want, which is this guy here, 2748.7. So 2748.7. And H3, what do we know about H3? It's 10 kilopascals and 88% quality. So we have a quality, we know we want to be at the tables. It's 10 kilopascals, so it's somewhere on this line here. And we're looking for the enthalpy. And we want it to be 88% of the way between HF and HG. So that would be 191.83 plus 0.88 times HFG, which is the difference between the two. So 2392.8, and I'm getting 2297.49. 2297.5, and these are all kilojoules per kilogram. Kilojoules per kilogram. Now, if we substitute everything into here, we should hopefully get the work done by the system. So let's see. M dot 3, which is 20.24 times 2297.5 plus M dot 2, which is 1.76 times H2, which is 2748.7 minus, because now we're not talking about what's going out, we're talking about what's going in. So minus the whole 22 kilograms at 3666.5, and I'm getting negative W equals negative 29,323. So multiplying by -1, I'm getting W equals 29,323.88 kilowatts, which means 29.3-ish megawatts. And that's how we do that.